Now, the last section we're going to talk about in this course is regression. Last time we talked about correlation. What is correlation? Last time we talked about correlation. What is correlation talking about? What are we looking for when we talk about correlation? And how's that related? So we're looking for what exactly there? The relationship between two variables. They come in ordered pairs. So all that told us, if there's a correlation, would tell us that what? What are we looking for here? What numbers are we looking for? Right. The correlation we're looking for is actually called the Pearson R value. It's between -1 and 1. The closer it is to 1 or -1, the more distinct all the data fits into a line. So if we're looking at these as graphs, those are examples of from -1 to +1 and all terms in between. That middle one be close to 0. So we're looking for a relationship between two variables. And that's what the R value tells us. Remember the formula for R? Yeah, that's that big one. N times summation of X minus the summation of X times summation of Y over square root, all this other stuff. So that just told us if there was a relationship. Now, regression tells us the line that is the best fit for that correlation or that relation. So we have this line is called the regression line. And it gives us the equation that best fits all that data. That's the regression line. It's the regression line is the line that best describes the relationship between all of the variables. So the regression, since that's a line, the regression equation looks like this. Y hat, that's called the hat, equals b sub 1 x plus b sub 0. You've seen this before in algebra. Since we're talking about a line in algebra is defined as y equals mx plus b. What does the m stand for? Very good. The slope of the line. And b stands for the, very good. B stands for the y-intercept. And that's exactly what B1 and B0 describe for us. B1 describes the slope between all the points and the y-intercept. Yes, don't close that door because people will be coming in. And it locks. All right. Now, I'm going to show you two ways of doing this. We can find the values of B1 and B0 by using formulas, or we can go ahead and let the computer do the work for us. And I'll show you both ways doing that. Of course, obviously, the computer is the fastest way of doing it. Actually, let's go and look at the first example. Yeah, well, the first example. The example we're going to be using is the chapter example, where we have this data set. Remember this one? The lottery tickets. So this is our data. This is our X values. This is our Y values. So example one says, use technology to find the regression equation. Okay, what is the regression equation? That's that y hat equals b sub 1 x plus b sub 0. So and on this bigger packet I gave you guys, I also gave you the steps you needed to find these. So what I did here first, I have all the data on columns 1 and 2. So let's first look at. Don't try to follow along. It's just you're gonna waste your time. And this always annoys me when students try to follow along and try to do it that way. Here are the formulas we'll be using. For the slope, that's b sub 1. R sy over sx. This is only one of the formulas. This is great because if you have technology, it'll do the work for you. So what do we know here? What is R? What is this R here? That's the R value, yeah. The linear correlation coefficient, or the Pearson R value. That's what we did last class. That has its own formula. What is S of X? What does S stand for? What does S stand for? Standard deviation of the X values from the sample. Yeah, these are defined the same way as we talked about them 15 weeks ago. What is S of Y? Well, it's the standard deviation of the sample of the Y values. So we find the R value, we find the S of X, S of Y, plug them in there. Now we need the y-intercept, the B sub 0. The y-intercept formula is y bar minus B1 times X bar. Okay, so now we have to ask, what does X bar represent? Yeah, it's the mean of the X values of your sample. And likewise, the Y bar is the mean of the Y values. How do you find the mean? Yeah. Add up all your values, divide by how many you have. That's X bar. And Y bar is the same thing. Add up all your Y values and divide by how many you have. Okay, so this is one way of finding out the slope and intercept. And referring back to the same format we had for R, the formula for B1 is N times the summation of X times Y minus the summation of X times the summation of Y over N summation of X squared minus the summation of X squared. If you looked at this very closely, that formula is very close to our R formula. Our formula for R has the same numerator, except the denominator is this equation inside square root, and it's multiplied to these, instead of X, it's Y's in a square root. And the y-intercept formula, using these summation symbols, is the summation of Y times summation of X squared minus the summation of X times summation of xy over the same denominator. And if we wanted to, we could figure out the value for r. And there's your value for r. And in that smaller packet, the smaller sheet I gave you, we're going to do these formulas separately. We're going to use the separate ones. So let's first, according to example one, it said, let's use technology to find our value for B1 and B0. So let me see what page it's on. Oh, on page 7. If you look at it on page 7, on the very top, I gave you the procedure on how to use stat disk to get those values. So in order for us to use, so our example one, example one said, use technology to find the regression equation. So what do we need to get first for our regression equation? What do we need? Well, it all depends on what formula we're looking at. We can try to do these, or we can try to do these. Which one's easier? Let's first go ahead and try to figure this one out. Because in order to do this, what do we need? We need r and the deviations of x and y. So where do we find the r value and the deviation of x and y? We go to analysis, like it says to find r, go to analysis, go to correlation regression. This is our x value. This is our y value. It's in the second column. We hit evaluate. It's going to give us everything we need to find the b sub 1. So b sub 1 is r s of y over s of x. So in this example here, what do we notice for our value for r? What is our value for r? Do you see anywhere here? What does R stand for? What's the name for it? Correlation coefficient. Do you see it anywhere there? Next to the top. correlation coefficient, R. It is R is 0.94735. So R is 0.94735. Now, there's something else on this page you could notice. What are we looking for this example? If you look at here, what is that telling us? What what do I have highlighted? What is that telling us? Okay, you're reading y-intercept. What else is it telling us? Keep on looking at all of it, the whole thing. It's giving me the entire formula. The regression equation has to have a B1 and a B0. What do you notice there on the two bottom on the blue box? What do you notice there? B1 and B0. So it tells us our B1 value is 0.17417. Our B sub 0 is negative 10.87169. So we can use this to find our equation. Our regression equation that's what the equation, that's what example one is asking us to find. We just found it. B1 is 0.17417 x plus our B sub 0. There is our regression equation. You don't have to write it all down. Everything's in the packet I gave you. You don't have to write it all down. If you don't believe me, let's take a look. It's right there. You can replicate it yourself. All you have to do is enter the data. The data is given in this packet and the last packet. But let's say we wanted to use our formula now. If we use this formula, will we get the same answer for B1? The answer should be yes, because why else would they give you that formula? So we know that R is 0.94735. We have to find S sub Y and S sub X. Where would we find those? Well, if we, again, the packet I gave you, go to data, go to explore data descriptive statistics, because descriptive statistics is going to tell us the mean variance deviation. For the first column, this is all the information for my X value. I have the mean, the median, the range, the variance, the deviation. I need the deviation, don't I? So S sub X is 70.50611. And I do the same thing for the next variable. I do it for the y variable. The standard deviation for the y variable, the second column, S sub y is 12.96255. So it's 12.96255, 70.50611. So we have 0.96255 times 12.96255 divided by 70.50611. We got 0.176965. That's our B sub 1. Is that the same value we got through the computer? No, through the computer, B sub 1 is 0.17417. Why is that? Why is there such a discrepancy? Well, it's rounding. It's what's that? Which one? When you did this one? Okay, it's 0.9. Oh, well, that's why 94735. I put that wrong. 94735. Now we got the right answer. But we'll talk about why they could be different if you do use those. And it has to do with rounding. So that's how we find the B sub 1. How do we find B sub 0? B sub 0, the formula for that one was y hat or y bar minus B1 times x bar. So where would I find x bar and y bar? Or how would I find it? Yeah, adding them, divide by how many we have. But they're given here. Y bar, this is the column 2, y bar is 26.55556. Y bar is the mean. It's 26.55556. And X bar is the first column. It's 214.8848 and a 9. So to find B sub 0, we take 26.5556 minus B sub 1, which is 0.17417. times our X bar put that in our calculator. Do 6.556 minus 17417 times 214.9. It gives us negative 10.8716. Which is the same thing we got up here. What's easier? Why would we show you both different ways of doing that? Yeah, in case you don't have technology, you can just use a calculator, which really bites. Because imagine if you had 50 or 60 pieces of data, you'd be doing this forever. So what is regression looking for? Regression is looking for a best fit line that describes the data. So if we go to correlation regression, we have our X values here, our Y values there. Evaluate those. Now, if we plotted them, there's the line that best defines the curve, that those data. It means a little bit more to it than that. Why is that line specifically in that position? Any guesses? But why is that specifically the slope of the data? Why are there points that are above there and there are points that are below there? And it has to do with the average. Yes. If we looked at each one of these, each point, the distance from the point to the line, the point to the line, the ones that are above it and the ones that are below it, what should happen when we compare them? If we added them all together, what should happen? Should be zero. Because anything above there is positive, anything below there is negative. So the average of all of those ones that are below it and above there, they should equal out. So positive and negative should equal, should be zero if I add them together. In your packet on page 8, making predictions. Regression equations often useful in predicting the values because remember, one of the purposes of finding this line here, because if we have this line, then we have an equation. What good is that equation for us? This is the best fit line. That's the best fit line. Again, why do they call it a best fit line? Because if we looked at the data, the average of all the points that are below it and all the points that are above it, they equal out and become zero. That's why it's called the best fit. But the beauty of this formula here is now I can put any value X I want to in there, and I should be able to predict what is the best value that should come up. Example, let's look at the packet I gave you, the small packet, the single sheet. Let's look at this example. Over there. You come in. It's always there. The example says, find the best predicted diastolic blood pressure for a person with a systolic reading of 122. So if you ever go to a doctor's office, you take your blood pressure, and it's always two numbers, diastolic and systolic. One of them records when your blood vessels start letting blood through it. Because when they put that sphygmomanometer, the cuff on you, they pump it up so it blocks off the blood. And then they slowly release it. And once it starts opening up so blood starts flowing, that's your first number. Then when they let it go even further and further until it starts moving so very freely, that's the second number. That's your systolic, is when it's open. Diastolic is what it takes to open it up. Now, what determines a good? Typically, they say 120 over 80 is a good number. 120 over 80, that's usually a good number. If you're an athlete, you're going to have something like 96 over 70 if you're a marathon runner, which means it takes nothing. Your blood flows very easily. So let's look at this. And this time, let's use our formulas, other formulas, to solve this. What formulas am I talking about? These guys. It's not gonna take all the time to do this. We're gonna set it up, and then I'm gonna tell you what the final answers are gonna be. But you're gonna start setting it up. What do you need to set up first? That's why I gave you all these columns and extra rows. Which one? Right. So we need summation of x and y. And those values, I have those. Summation of x is 1875. And the summation of y is 1241. So just add them up. That's summation means just add them up. Now, looking at your formula, what else do we have? So what we have right now, we have summation of x, summation of y. Where else can we use the summation of x, summation of y's? Well, not yet. Here's a summation of x here. We can use those values there. Summation of x squared. Whatever summation of x is, whatever that final answer is, which is 1875, this one says take that 1875 and square it. That goes down there. So I'll put the formula down. And as we start filling them in, and B sub 0, doing both. And if you notice, they both have the same denominator. What is our n? Hmm? How many pairs of numbers? How many pairs of numbers do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So n is 14. So anywhere I see an n, I put a 14. On the very top, we know the summation of x and summation of y. Summation of x is 1875, and 1241 is the summation of y. Here's a summation of y, so that's 1241. There's a summation of x, 1875. $18.75 squared. 1875 squared. So what else do we need to complete our equations? How many more columns do we need? Yep, we need summation of x times y. So we have to have here x times y. And those are going to be pretty big. Let me see it. So the summation of x times y. Once we do this times this gives us that. This times this gives us that. We add them all up. That equals 167,023. So that's 167,023. Now we need what? We need summation of x squared, because that's top and bottom here. So we need to have an x squared. How do we find x squared? Take the value in the x column and square it. So it's 138 squared, whatever that's going to equal, 130 squared, and then so on and so forth. Add up all those. We get 252,179. Two 52,179. So if we were to put this in the calculator and we type everything correctly, we should come up with our B1 value should be 0.77. Which one? Down here? Because it's summation of x squared. Yeah, that's a good question. The squared is outside the parentheses, so you do the summation first and then square the answer. And then if we do this on the b sub 0, we get negative 14.38. So for our y hat, we get b sub 1x plus b sub 0. Our y hat is 0.77 times x minus 14.38. This is the formula. That's the formula we use to predict any future occurrences. So what do we plug in there? We did all that stuff just to find a formula. Now what do we do with that formula? Well, the question says, find it for a person with a systolic breathing of 122. We plug in 122 there, so our y hat is 0.77 times 122 minus 14.38. And that's going to give us a value of 79.56. That's our prediction. That's what the y hat is our prediction. There's a difference. The y hat is a prediction. The y is our observed. This will be important when we start talking about it in a second. We did something like that, so we don't need that. So far, so good. So once we have our formula, our y hat, marginal changes. What is a marginal change? A marginal change is what happens to the value, what happens to our equation when we change the x value by 1 unit. What happens to a predicted value when x is changed by 1 unit? So in our example we had here with the blood vessels and everything, we had 0.77 times x minus 14.38. So when we put x is 1 inside there, 0.77 minus 14.38. Our marginal change for each unit change in our equation is we have a net loss of 13.6 blood pressure points. That's outcome. We'll look at our equation. That's what we'll look at for each small change that occurs. Influential points. A point is influential if a change, if by adding that number into our data set, if the change is considerable, then that point is influential. By adding 1 point, by adding 1 point to our data set, if that changes our values considerably, then that's influential. An example of an influential point is an outlier. What is an outlier? A point far away from the other data points. Let's look at this. Let's see what this means. We right now, in our data set, we have this regression line. What if we go back to our data and we add another point? 980 and 12. Okay, we still have the X column in the first one, Y column. So here's our information. We have a regression line. Let's see what happens to the plot. Is that considerable change in the graph? Yes, because it's one outlier all by itself over here. This is the reason why outliers are no good in data sets. Even though it may seem like it's just a little bit out, it may be far enough out that this is an extreme case, of course, but we're looking at, is that going to cause a problem? Yes. So what do you do with that? What do you do with outliers? Usually we just get rid of them, because since they are outliers, they are some sort of anomaly to the data. So either whoever recorded them did incorrectly or whatever. So we just get rid of it. Now, remember when we talked about we had the best fit line and we have the data points. And we talked about if we looked at all of these distances from the points themselves to the line, the average of all those should be equal if it's a best fit. Those are called residuals. A residual is defined as the difference between the observed values and the predicted. values. Now, remember, each point has an X and Y. Which one of these ordered pairs are we looking at? Are we considered with? When we talk about the observed values and the predicted values, we're talking about the Y values. Because X is just at what point do we observe them? So when X is, say, 1, the actual, the observed one versus the predicted one are two separate ones. So that's what we're looking at. These are the Y values. So the residual is equal to the Y minus Y hat. That's the formula for the residual. Observed is the Y's you have in your data set. The predicted are the Y values. Remember, once we calculated this, then we have our predicted. These are predicted. All right, so look at a small example of these. Here's our data set. When X is 8, it's 4. When X is 12, it's 24. 20, it's 8. 24, it's 32. And our Y hat is 1X plus 1. So B1 is 1 and B0 is 1. So here we have our X values, our Y values, and our Y hats. Observed and predicted. So we have 8, 4, 12, 24, 28, 24, 32. Remember, the Y hat is X plus 1. So in this one, it's 8 plus 1. This one would be a 9. This is 12 plus 1 is 13. 20 plus 1 is 21. 24 plus 1 is 25. How do we find a residual? What's the formula for residual? Y minus Y hat. So 4 minus 9 is negative 5. 24 minus 13 is 11. 8 minus 21 is negative 13. 32 minus 25 is 7. Remember what we talked earlier. So what do the residuals represent? Yeah, the distance from the data points to the best fit line. And what should happen? The ones up here should equal the ones down here. If we added all these together, what do we get? So that means because of that, that's our first check. Because it equals 0, that means it is the best fit. That means y hat x plus 1 is the best predictor that we can have. Now, what we're looking for is, because it's the residual we're looking for, the square, the sum of the squares of all the distances has to be the smallest possible number. Because, yeah, we know it's good because it equals 0. But what the least square does is we take each of these numbers and square them. And then add them up. This is sum of the least, sum of the squares of residuals is the smallest possible number. That's called the least squares. So we have 25. 11 squared is 121. 13 squared is 169. 7 squared is 49. So that's 290. That's 290. No, 390. 290, yeah. 25 plus 49 is 74. So it's 364. This is the least square of the residuals. Can we plot those? How about a residual plot? What would that graph look like? Originally, we have X and Y as our points. But since we're looking at residual, we're looking at X and Y minus Y hat. So let me see if I have those ready. Yeah, so here's my Y values. This is my Y hat. So that's my residual. So if I took my first column and my fourth column, oop, these guys ruined it. And I plotted them. Ideally, it should be horizontal. Ideally, it should be horizontal. And last part of your sheets. If it's a horizontal and the data is scattered throughout, then the residual plot suggests that the regression equation is a good model. We can use it for future events. If the data creates some sort of graph, some kind of line, then the residual plot of an obvious pattern, it's not a good model. In other words, the data themselves are not random to begin with. They seem to be following some sort of pre-designed pattern. Or if this is what we call diverges. If the data diverges, meaning it gets farther and farther apart, then it's not a good model. So this is one reason we do a residual plot, to see if it's a good model or not. What do we mean by model? It means a model simply means a mathematical formula that defines what you're looking at. So if you want to look at the blood pressures, is there a mathematical model that best defines the systolic, the diastolic? Is there a perfect way we can observe these so we can make prediction of what, or if you have 120 systolic, what should your diastolic be? Or if you have 180, what should your other ones be? That's what when we talk about models. A model is a mathematical prediction of future occurrences of the events you're looking at observing. Any questions? That's the end. End of semester, end of section, end of chapter, and end of course. You're supposed to stop recording. Stop recording.